The human average for attributes is 3. That was what I said in the Shadowrun 4th edition basics video. Though that doesn't necessarily tell us much about the likelihood of success, especially since dice pool systems don't quite have the same sort of intuitive probabilities as their more simpler roll dice and add modifiers counterparts. Not that this simplicity has led to an understanding of probability amongst your typical D&D or Pathfinder player. A shame, since theirs is mathematically the simplest of dice systems. You have a 20-sided die, you already know your modifiers, and with that you can easily figure out how likely you are to get a certain number or higher when you roll. And to make matters easier, it'll always be a 0% chance or some multiple of 5%. Put into action, an enemy has an armor class of 15. You know your 2-hit is 7, meaning you need at least an 8 to connect, meaning 7 or lower will be a miss, multiply 7 by 5, and you have a 35% chance to miss, and if we take the inversion of that, it's a 65% chance to hit. Folks with dyscalculia or other problems with performing mathematics, on the other hand, may prefer dice pools. Especially since in this case, you can paint your success results on the dice a different color from all the other sides, and simply look for colors instead of numbers or counting pips. I've even heard people say that this is all around simpler mathematically. You're counting up how many reach a number. How could it possibly be harder mathematically? These people I do not stay on friendly terms with. You see, to determine the probability of dice pools, you need the binomial distribution formula, which is this thing right here that I found over at Statistics by Jim. Yes, every time I look at it, I wind up confused too. But let's think of this as no different than learning any other tabletop role-playing game. We take it one piece at a time and then worry about how it all fits together as we go along. And I can see 3 distinct parts we're going to need: NCX, p to the power of x, and 1 minus p to the power of n minus x. And NCX has an expanded form we can work through, since that's just the combination formula, a way to figure out how many different combinations you can get from a larger set of items, where the order of the items is irrelevant. When we have those 3 figured out, we multiply them together, and that's our percent chance. If you remember your basic algebra, every letter here can be replaced by a specific number. And the letters here are as follows. N is the number of trials. In this case, how many dice we're going to roll. X is the number of successful trials. This is how many hits we're looking for. And P is the probability of success, how likely we are to get 1 hit. Let's just cook up a scenario in Shadowrun to turn these abstract ideas into specific numbers. Let's say we've got a pistol's rating of 6 and agility of 6, and we're armed with a Facchetti security, a light pistol perfect for people who hate having to deal with the indignities of reloading in the middle of a firefight. And if we're using a laser sight, that creates a dice pool of 13, since that gives us a +1 when we're using the laser sight. 13 is N, the number of trials, since each die counts as 1 trial. For how many hits we need, let's say we're trying to guarantee that an average goon with a reaction of 3 is going to get hit. Since ties go to the defenders, we'll need at least 4 hits. That's X. Each hit is 1 successful trial. Last, we need to know how likely it is to get 1 hit on 1 die. This is the easiest one to figure out. We're using D6s, which have only 6 sides. Only 2 of those sides will give us a hit, 5 and 6. So it's 2 divided by 6. This is P, and that is how likely 1 hit on 1 die is going to be. Now that we have our numbers, we can start crunching them. That exclamation point next to N and X in the formula is factorial. When you see that, you take the number in question and multiply it by every number that leads up to it from 1. Thus, the top part of NCX is going to be 1 times 2 times 3 times 4 times 5, so on, up to and including 13. This gives us a really big number, 6,227,020,800. The bottom part, we have a parentheses, so we solve what's in there first. N is 13, X is 4, so we have 9. We factorial that, and we factorial 4, and multiply these 2 factorials together. This gives us the less big 8,709,120. And then we finally divide the top half by the bottom half, and we have a much more reasonable 715. Let's set that aside and work on the next part of the equation. P to the power of x. P, as we discussed, is 2 over 6, 0.3 repeating. Then we just raise that to the power of 4, which is 0.01234567 repeating. We'll just stop at the 9 there, since what we're figuring out is something for a silly little game of pretend, and we don't need that much accuracy. Set that number aside, and we move on to the next part of the equation. This next section is similar to the previous. We'll start with 1 minus p, which is 0.6 repeating, and we raise that to the power of n minus x, which we established earlier to be 9. Altogether, that's 0.026012294. It's long, and I don't think this thing terminates. But with this third piece, we simply multiply everything together now, which is 715 times 0.01234567 times 0.026012294. All that together gives us 0.2296. Multiply that by 100 and we have something close to 23, the percentage chance that we will get those 4 hits we need with 13 dice. And this is why dice pools are a nightmare to calculate probability for. You have a much longer formula you're working with. Now, for those of you more comfortable with mathematics, you might have noticed that I took the long way around for a lot of this. And you are right. There is a few shortcuts we could have taken to simplify this. But if you have one of those programmable scientific calculators, you can just set up this formula for it, punch in the numbers, and let the mathy thinky brick do the hard work for you. Or the one I know you can do with relative certainty since you're watching this video on a device that has access to a web browser, go find a binomial distribution calculator on the internet and use that.